Hello, welcome to the video lesson. And video notes for lesson 10-5. I know it says 11-5 at the top of the page, but that's a typo. It is supposed to be 10-5. This lesson is about functions and tables. The learning targets: I can recognize a function from a table, and I can determine the average rate of change. So we're going to be talking about how to find the average rate of change. Now, recognizing functions is pretty simple. We have some examples on this first page. So, oops, don't need that. Pair the following functions with its corresponding table. So we're looking at either a linear, quadratic, or exponential. Essentially what you need to do is look at the table and see what's happening. For all the x values, that's pretty simple. They're all just merely increasing by 1 every time. So the input, or the x values, are not what gives this away. It's what happens to the output that will help you determine which function you're dealing with. And I know my plus ones are a little sloppy. I'm not focusing on that. Alright, so to go from 1.5 to 3, some of you might say, oh, well, I added 1.5. Okay, well, not so much. Going from 3 to 6, you wouldn't add 1.5 again. Actually, if you look close enough, you probably recognize that we are doubling. Times 2, times 2, times 2. So, what kind of function doubles every time, or triples, or quadruples? That is exponential. And then, you know what? Let's just go ahead and do the equation for this. F of x equals my initial value, my y-intercept is 3, 0, 3. So 3 times my base, or my growth factor, is 2. So 2 to the x. The next one, when I'm looking at it, this is increasing with a nice constant rate of change of 2. So this is clearly linear. And the y-intercept is at 0, 3. So if I'm making a function or equation for a function rule or an equation, f of x equals, because it's increasing by 2 every time, there's my rate, or my slope, 2x, plus 3 is my y-intercept. And then, so obviously this is going to be my quadratic. Notice what it does. It goes down 3, goes down 1, then it increases 1, increases 3, increases 5. If this had continued above this one, it would be subtract 5. So clearly this is the quadratic. Hopefully you watched the video on the vertex form video that is at the beginning of this topic. F of x equals x plus 1 squared. Now, there would actually be a plus 0 here, but we don't need to add 0. But for those of you that understand vertex form a little better now, you may have a better understanding where this formula comes from. Another way this formula could be written is f of x equals, if I want to expand that, x squared plus 2x plus 1. But we don't need to expand it. This is fine. Okay. Now, below is 3 more examples. I'm actually going to let you try these on your own. You're going to graph all of these and see what they look like and identify whether it's linear, exponential, or quadratic. But we don't need to do that together, because that is something that I want you to practice on your own. Alright, so this is everything for page 28. Let's go ahead and take a look at page 29. To recognize if a function is linear, quadratic, a parabola, or exponential without an equation or graph, look at the differences of the y values between successive integral x values. If the difference is constant, the graph is linear. If the difference is not constant, but the second set of differences are constant, the graph is quadratic. If the difference follows a pattern similar to the y values, the graph is exponential. Now, when we say pattern, we're looking for doubling, tripling, quadrupling, all that kind of fun stuff. All right, so when you see our examples here, this reinforces what's above here. So this first part goes with example 1, this goes with example 2, this goes with example 3. So when we're looking at this, we've got a constant rate of change, the first set of differences. That's why this one's linear. Now look at this. So for the quadratic, when you find the difference in the y values, -5, -3, -1, 1, 3, 5. So it goes down and then goes back up. And that's how you can kind of tell the quadratic pattern, if you will. But then look at, if we then take these values and find the difference, then it's going at a constant rate of change, kind of like linear. But it isn't the first set of differences, it's the second. So here's the first set, and then the second set of differences, that's what this is called, talking about here, is constant. Then that's a quadratic. In other words, that's how we have these points mirroring each other on either side of the axis of symmetry. And then below, this is clearly a pattern that is doubling. And when you double or when you triple, you are multiplying by a specific number, or a base, if you will. And that is how we get our exponential relationship. These are just the examples from the front, again, reinforcing what we just looked at up above. So here's our +2, +2, +2, +2, +2, our constant rates for the linear. Here with the quadratic, it's -3, -1, +1, which is what we saw up above anyway, so +3, +5. Now, you could probably pick up on the quadratic from this, but if not, try taking the second set of differences, and you'll notice that it's constant. That makes it quadratic. So second difference is constant. And then again, our example from the front, or from page 28, I'm sorry. This time we're multiplying by 2, or doubling. And when your pattern is multiplying, it is exponential. Doubling, tripling, quadrupling, whatever you want to call it. All right, pretty simple stuff. Okay, on the next page, we're going to take a look at something a little different. Average rate of change. We quantify how one quantity changes with respect to another using average rate of change. So, when you find an average, you are essentially dividing one number by another. The numbers that we're going to be getting here are going to be the change in f over the change in x. In other words, we're going to do the change in the output over the change in the input. You may remember doing this when we would find slope, change in y over change in x. Another way to think of it is we are going to f of x2 minus f of, there's a minus there, x1. So that's kind of like y2 minus y1 over the second x value minus the first x value. The average price for, so we've got an example here we're going to try. The average price for a ticket to a movie theater in North America for selected years is shown in the table below. How has the price of movie tickets changed from 1990 to 2014? So to answer this, we're going to do these examples at the bottom, or parts A and B here, I should say, and then come up with a conclusion. Find the average rate of change for a ticket price with respect to time over the periods 1990 to 2002. So we're not going to be taking all of these. Oh, there's a terrible star. Let's try it again. There we go. We're just going to focus on this group and this group first. So here's our f of x. I'm sorry, that is not our f of x. The years are the input. The price is the output. That's our f of x. So the dollar values are going to go on top. So I always like using delta y over delta x, or changing y over changing x. So I go with the second value, 580 minus 422 over 2002 minus 1990. And when you do that, you get 1.58, or 1 and 58 over 12. When you divide it, you get about 13 cents per year. And it's a positive number, so that means we're increasing. Now we're going to do the same thing, but going from 2002 to 2014. So again, changing y over changing x, changing f of x over changing x, whatever you want to call it. So we got 8, 17, take the second one minus the first one, 580 over 2014 minus 2012, or 2, I'm sorry, and we get 237 over 12, and that, oops, we want to say, is approximately 20 cents per year. Okay, what does that mean? Conclusion. Well, it's pretty simple actually. The price of movie tickets are increasing. Now, some of you may be thinking, well, we only do this when it's a linear relationship. No. Finding the average rate of change you can use with any kind of relationship. You just are essentially using the end values, the starting and ending values, and subtracting and finding the average by dividing. All right? Pretty simple math, actually. So from 1990 to 2002, there was an average increase, and it was increased because it was positive, of 13 cents per year. Should be a decimal there. And from 2002 to 2014, an average increase of 20 cents per year. All right, and that's it. So hopefully you should have enough information now to work on the practice problems over the next couple pages. If you have any questions or don't understand anything, something about this, I'm sorry, go back and rewatch the video. Good luck, and we'll see you in math.